Imagine you're stranded in the middle of a perfectly frictionless frozen lake. Like, your shoes have zero grip. None.
Yeah, that's a pretty terrifying thought.
Right? You can't walk, you can't crawl, you can't even push off the ice. And there's absolutely no wind to blow you toward the shore either.
You're just completely stuck.
Exactly. So how do you get off the ice? Well, the answer to that riddle involves the exact same physics that allows a 3,000-ton metal skyscraper to fly to the moon.
It really is a mind-bending puzzle. But solving it, I mean, it completely reframes how we look at spaceflight. We're taking a deep dive into the underlying physics of rocketry today.
Stripping away all that noise and the fire and, the overwhelming technical jargon, we really want to just look at the raw mechanics underneath it all.
Yeah, because we've all seen the footage of a launch, right? The countdown, those massive clouds of smoke, the deafening roar that literally vibrates in your chest.
Oh yeah, it feels completely impenetrable. But the sources for this deep dive promise something really cool for you today. Underneath all that spectacle, there's a surprisingly elegant, simple trick.
And once you grasp that trick, you will never look at a rocket launch the same way again. I promise you that.
Because getting to space is much less about, just flying upward into the sky and much more about mastering one fundamental law of nature. And you really don't need any prior science background to get this today.
Not at all.
Okay, let's unpack this. Because to get to that fundamental law, we first need to address a huge trap that, honestly, most of us fall into.
Oh, definitely. The push trap.
Yeah, exactly. When I think about moving forward, whether I'm walking or swimming or driving, I'm always pushing against something.
Right, there's always a physical surface.
Yeah, like in a pool, you push your feet against the wall to shoot forward, or a car's tires push against the asphalt. So watching a rocket lift off, the brain naturally assumes the rocket is pushing against the launch pad, right?
It's the most logical assumption you could make. I mean, based on everyday experience here on Earth. But if that were true, spaceflight would be entirely impossible.
Because there's nothing to push against in space.
Exactly. Think about the environment of space. If a rocket relied on pushing against the atmosphere, like a swimmer pushing against a pool wall, it would become completely useless the moment it reached a vacuum.
Right, because there is literally no air out there. The pool wall is just gone.
It's gone. In fact, our sources point out rockets work perfectly well in a vacuum. Actually, they work even better up there without all the air resistance dragging them down.
Which completely breaks my mental model, I'm not going to lie. If there's literally nothing to push against in space, what is moving the rocket?
Well, this brings us back to that frictionless frozen lake you mentioned, and to Newton's third law of motion.
Ah, the classic. For every action, there's an equal and opposite reaction.
That's the one. People memorize the phrase, but applied to rocketry, it is intensely practical.
The sources use a great visual for this, which really helped me. Imagine you are standing perfectly still on a skateboard, and you're holding a really heavy bowling ball.
Okay, I'm picturing it.
If you throw that ball as hard as you can straight out in front of you, what happens? You roll backward.
Exactly. You didn't push against the ground. You didn't push against the air.
No, you just shove the mass of the ball. And the act of violently shoving that mass one way, well, it shoves your mass the opposite way.
Which solves your frozen lake riddle, by the way. If you took off your heavy winter coat and threw it as hard as you could in one direction,
you would slowly slide in the other direction.
Yes. That backward slide is the entire foundational secret of rocketry. A rocket is basically just a giant machine engineered to throw stuff out of its back end as aggressively as possible.
But a rocket isn't throwing bowling balls or winter coats out the back. It's throwing fire and smoke. And I guess I struggle to see how gas provides enough mass to lift something that weighs, millions of pounds.
It works because it is a phenomenal amount of gas, and it's moving at supersonic speeds. Inside a rocket engine, you basically have a highly controlled, continuous explosion.
A continuous explosion? That sounds terrifying.
It kind of is. When you burn rocket fuel, it reacts and expands violently. That expanding, scorching hot gas desperately wants to escape in every direction.
So if you just ignited it in the open, it would just be a chaotic fireball?
Exactly. It wouldn't go anywhere useful. The engineering magic happens with the rocket's nozzle.
Oh, you mean the big bell-shaped cone at the bottom of the engines?
Yes, that bell shape isn't just for show. It acts as a trap and a funnel. It takes all that violently expanding gas and forces it to exit in only one direction, straight down.
Okay, so by constricting the flow and then letting it expand along the curve of that bell shape, the gas accelerates to just incredible speeds.
Precisely. The technical term for that upward shove you get in return is thrust.
So the high-speed gas is essentially the bowling ball. By throwing tons of hot exhaust downward at thousands of miles an hour, the rocket gets shoved upward.
And because the rocket is creating its own thrust simply by flinging its own exhaust away, it doesn't care if it's in the atmosphere or in the dead vacuum of space. It is entirely self-reliant.
Okay, here's where it gets really interesting. Because if the whole trick is just burning fuel to create expanding gas and shooting it out a nozzle, that sounds an awful lot like a commercial jet.
They do have some similarities, sure.
People lump rockets and jet planes together all the time, right? Aerospace. Which makes me wonder, why do we need entirely different vehicles? Why couldn't we just, I don't know, take a 747, point the nose straight up, and fly it to the edge of space?
You run into a severe chemical problem almost immediately if you try that. To create that continuous explosion, to make fire, you need oxygen.
Right, fire needs oxygen.
And a jet engine is fundamentally a giant breathing machine. As a 747 flies, those massive turbine blades at the front of the engine, they scoop in air from the surrounding atmosphere.
Oh, so it compresses that outside air, mixes it with jet fuel, and ignites it to create thrust.
Basically, yes. The outside air is a non-negotiable part of the chemical reaction for a jet.
So it's using the sky itself as half of its fuel supply.
That's a great way to put it. So as that 747 points up and climbs higher, the atmosphere gets thinner and thinner.
Right, there's less air.
Exactly. Eventually, there simply isn't enough oxygen to sustain combustion. The engines choke, the fire goes out, and your thrust drops to zero. Jet planes are literally physically tethered to the Earth's atmosphere because they have to breathe it.
Wow. Which means a rocket must bring its own oxygen with it.
Exactly. A rocket packs everything it needs to survive where there is no air. It buys its total independence from the atmosphere by carrying both halves of the chemical equation.
That's so gloriously self-contained.
It really is. In rocketry, we actually make a crucial distinction between the words fuel and propellant.
Oh, I always just use them interchangeably.
Most people do, but we use propellant as the umbrella term for the total package. Propellant consists of the fuel, so like liquid hydrogen or highly refined kerosene, plus what we call an oxidizer.
Got it. So the oxidizer is the stand-in for the atmosphere.
Right. It's the chemical substance that supplies the oxygen, so the fuel can actually burn in space.
But to pack enough oxygen to feed these massive engines for minutes on end, you can't just carry, like, a few scuba tanks of compressed gas, right? Not even close. You have to chill oxygen down to nearly 300 degrees below 0 Fahrenheit.
Whoa! 300 degrees below zero.
Yeah. You chill it until it condenses into a dense, heavy liquid oxygen.
Okay, I see where this is going, and it feels like a massive design flaw. Liquid oxygen sounds incredibly heavy.
Oh, it is remarkably heavy.
So to solve the vacuum problem, you've just added an immense amount of dead weight to a vehicle whose only job is to fly upward against gravity.
What's fascinating here is that you've just stumbled onto the defining nightmare of aerospace engineering.
I have.
Yes, it's a concept famously known as the tyranny of the rocket equation.
The tyranny of the rocket equation. That sounds dramatic. It's brutal. The physics creates this vicious compounding cycle. To lift a heavy vehicle off the launch pad, you need a tremendous amount of thrust.
Right, that makes sense.
But to generate more thrust, you have to burn more propellant. And that extra propellant adds massive weight to the vehicle.
Oh, no. So now the vehicle is heavier, which means you need even more thrust to lift it.
Exactly. Which requires even more propellant. You see the problem.
You're just chasing your own tail. I'm looking at the map on this from our sources, and it feels like a complete dead end.
Yeah.
How do you ever actually get a payload, like a satellite or a crew capsule, off the ground?
The margins are unbelievably slim. Because of this tyranny, when a rocket is sitting on the launch pad ready to go, the vast majority of its bulk is not the payload.
The spacecraft and the astronauts are just a tiny sliver perched at the very top.
Right. Around 90% of the rocket's total weight is purely propellant.
90%. So it's basically just a giant fragile metal balloon filled with explosive liquids.
A flying fuel silo, that's really what a rocket is. But wait, if the rocket is 90% fuel, once it burns through half of it, isn't it just wasting precious thrust hauling around gigantic empty metal balloons? That seems terribly inefficient.
That is a brilliant observation.
Yeah.
And you're completely right. A few minutes into the flight, the engines have guzzled through half of that liquid propellant. Now, the bottom half of this enormous metal silo is completely empty.
So you're dragging hollow, giant steel tubes into the upper atmosphere. That has to just drain whatever precious thrust you have left.
It drains it so fast that a single continuous rocket tube, practically cannot reach space with any meaningful payload.
Really? You just couldn't do it.
You'd run out of fuel before you reached your destination, purely because you were hauling the empty containers. The engineering workaround for this inefficiency is called staging.
Okay, staging. Our sources use a great everyday analogy for staging that finally made this click for me.
Oh, the mountaineer one?
Yes. Imagine a mountaineer trying to summit a treacherous peak, like Mount Everest. They start at base camp with a massive backpack full of food, oxygen, and gear. Right, they need all of that to survive the early parts of the climb.
But as they climb, they eat the food and use the oxygen. They wouldn't keep carrying the empty oxygen canisters and empty food wrappers all the way to the summit, right?
That would just be dead weight.
Exactly. They drop the dead weight along the trail so they are lighter for the final hardest part of the climb.
Staging is doing exactly that, but at supersonic speeds. Instead of a single hollow tube, engineers build rockets in separate, independent sections stacked on top of each other.
And each section, or stage, has its own fuel tanks and its own engines.
Exactly. So the rocket lifts off using the massive first stage at the very bottom, and when that bottom stage depletes its fuel load, explosive bolts fire.
Whoa, explosive bolts.
Yes, the entire empty bottom section just detaches and falls away. The rocket actively sheds the dead weight.
So it's dropping the empty backpack.
Exactly. And immediately, the engines on the second stage ignite. Because the vehicle is suddenly drastically lighter, the remaining fuel in the upper stages is far more effective.
It can just continue accelerating without being dragged down by empty metal tanks. It's a brilliant way to cheat the rocket equation.
It really is. You just throw away the parts of the vehicle you don't need anymore. It's the only practical way we've found to leave the atmosphere.
Okay, so staging gets us past the weight problem, which means we can finally keep our engines burning long enough to actually leave the atmosphere.
Right.
So what does this all mean for the actual path to space? Because if you watch a rocket launch, you'll notice something weird happens a minute or two after liftoff.
It doesn't go straight up.
Right. The rocket doesn't keep flying straight up. It starts tilting. It pitches over and begins flying sideways. Why fly sideways if the entire goal is to go up into space?
Well, because going, quote unquote, up into space isn't really the goal. It's just the prerequisite.
Wait, what?
Yeah, if you want to understand spaceflight, you have to realize that space itself is remarkably close to us. The generally accepted boundary of space is called the Kármán line.
Where the atmosphere effectively ends and the vacuum begins.
Exactly. And it is only about 100 kilometers straight up.
100 kilometers. I mean, if you could drive a car straight up at highway speeds, you would be in space in about an hour.
An hour's drive. Getting high up is actually the easy part. If a rocket just flew straight up to 100 kilometers and shut off its engines, it would reach space, experience a brief moment of weightlessness, and then plummet straight back down to Earth.
Because gravity never stops pulling.
Never. The true mountain a rocket has to climb isn't altitude. It is speed. Specifically, sideways speed.
To get into orbit.
Yes.
But what does that actually mean? Because I think a lot of us, we picture orbit as floating in this zero gravity zone where Earth's pull somehow just doesn't reach you anymore.
That is a huge misconception. Gravity is very much still pulling on you in orbit. In fact, gravity is the only thing keeping you in orbit.
Okay, you're going to have to explain that one.
If we connect this to the bigger picture, we can look at a famous thought experiment by Isaac Newton. He imagined a cannon sitting on top of an impossibly tall mountain firing cannonballs.
Okay, so if you fire a cannonball normally, it flies forward for a bit, traces a curved path, and hits the ground.
Right. And if you put more gunpowder in the cannon, the ball shoots out faster. It travels much farther before gravity eventually pulls it down to the dirt.
Makes sense.
Newton reasoned that if you could fire the cannonball fast enough, something incredible would happen. Remember, the Earth is a sphere, so its surface curves downward.
Right, it's not flat.
Exactly. If the cannonball is flying sideways at an extreme speed, it is still falling toward the ground, but the ground is curving away underneath it at the exact same rate.
Wait, so the ball falls, but the Earth curves away. It falls again, the Earth curves away again.
Yes. It is constantly falling, but it never actually hits the ground. You just keep missing it.
That is wild. So that is what an orbit is. It's a permanent, graceful fall around the planet.
Exactly. You are always falling. You're just moving sideways so incredibly fast that you continuously miss the Earth.
And to miss the Earth, our sources point out you have to be moving at 28,000 kilometers an hour.
28,000. It's astonishing.
That is the magic number to outrun the curve of the planet.
And that sideways sprint is what devours almost all of the rocket's fuel. Escaping the thick lower atmosphere is really just about getting out of the air, so atmospheric drag doesn't burn you up when you accelerate.
The real energy is spent going sideways.
Precisely.
It is mind-bending to realize that the astronauts on the space station, they aren't floating because they are free from gravity. They are floating because they are inside a metal can that is falling forever, and they are falling along with it.
It is a continuous state of free fall, sustained purely by sideways momentum.
What really stands out to me in the source material is the timeline of all this. Because the core physics here, using exhaust mass as a bowling ball to push the skateboard action and reaction, it's ancient.
Oh, absolutely. The Chinese were launching solid-fuel gunpowder rockets as weapons and fireworks nearly 1,000 years ago.
1,000 years.
Yeah, the foundational mechanism hasn't changed a bit since those first fireworks. The physics of throwing mass out the back to push forward was being utilized centuries before Newton even defined the laws of motion.
So why did it take a millennium to go from fireworks to orbiting the Earth? I mean, if the physics is ancient, what was the holdup?
Well, the physics was simple, but the engineering required to hit 28,000 kilometers an hour is monstrously difficult.
Ah, the engineering caught up.
Right. We had to wait for the 20th century to develop engines powerful enough, lightweight materials advanced enough, and computer guidance precise enough to actually survive the tyranny of the rocket equation. We finally figured out how to build staging mechanisms reliable enough to shed weight mid-flight.
But dropping those stages introduces a huge modern problem, which is cost. For decades, when a rocket dropped its massive multi-million-dollar first stage, that empty metal silo just plummeted into the ocean to sink.
It was gone forever. It was a necessary sacrifice to reach orbit, but economically, it was devastating.
This raises an important question about the sheer cost of spaceflight. The sources make a comparison that is genuinely painful to think about. Imagine you want to fly from New York to London.
Okay.
You buy a ticket, you board a commercial 747, and you fly across the Atlantic. When you land in London, you step off, and the airline immediately pushes the entire 747 into a giant shredder.
Just throws the whole airplane away.
Right, after one single flight. To fly back, they have to build a brand new, multi-million-dollar airplane from scratch. The cost of a ticket would be astronomical.
And that disposable model is exactly why access to space was historically limited to global superpowers with bottomless tax revenues. You were throwing away the vehicle every time you used it.
Which brings us to the biggest shift in modern aerospace: reusability. Instead of letting those massive lower stages crash into the ocean, engineers are now bringing them back.
Reusability is fundamentally altering the economics of space. We're now seeing first stages separate, flip around in the upper atmosphere, reignite their engines to slow down, and autonomously navigate to land perfectly upright.
On those concrete pads or floating drone ships. I watch those videos and my brain still struggles to process it. It looks like footage being played in reverse.
It is an unbelievable feat of software and engineering. By flying the most expensive parts of the rocket back home, refurbishing them, and launching them again, the price per pound to orbit is plummeting.
It opens up the frontier to commercial businesses, smaller satellites, and ambitious deep space missions that were just previously impossible to fund.
Exactly. But, even as we watch a 15-story metal booster steer itself through the atmosphere to land precisely on a ship at sea, the core trick driving the whole thing is still just a bowling ball on a skateboard.
We're just using much fancier bowling balls.
Exactly. We are applying 1,000-year-old physics with breathtaking 21st century precision.
So let's tie this all together. The next time you see a rocket launch, I hope you look past the noise and the flames, because you know what is actually happening underneath it all.
You aren't just watching a machine fly up.
No, you're watching a vehicle operating in total independence, carrying its own chilled liquid oxygen and violently throwing its own mass downward to force itself upward.
You're watching it methodically shed its empty supply packs, dropping dead weight so it doesn't get trapped by the tyranny of its own mass.
And, its true goal is to tilt over and sprint sideways at 28,000 kilometers an hour, racing to outrun the curve of the Earth so it can fall gracefully around the planet forever.
It is a profound perspective shift on one of our greatest engineering achievements.
It really is. And I want to leave you with one final thought to mull over. Building on this idea of orbit as a continuous sideways fall. On Earth, because our planet's gravity is so incredibly strong, it takes a massive tower of explosives to reach the speed required to miss the ground.
Right.
But orbit is just a ratio between your sideways speed and the gravity pulling you down. Imagine you are an astronaut standing on the surface of a tiny asteroid deep in space, a small rock with incredibly weak gravity.
Okay, I'm imagining it.
If the gravity pulling you down is slight enough, the sideways speed you need to miss the ground drops dramatically. On a small enough asteroid, could you achieve a permanent orbit simply by sprinting and jumping sideways?
Wow.
Imagine that. No engines, no fuel tanks, just gracefully falling around a rock in space, powered entirely by your own two legs, achieving orbit with just a running start.
That is incredible to think about.
Thank you so much for joining us on this deep dive. Take care and keep wondering.